Uh, so just to recap, we looked at, we started today with introduction to tau, the different modes of instrumentation. We looked at how we can easily instrument a MPI application, an MPI application using tau exec-EBS. We looked at CoMD. We saw with MPI only and MPI with OpenMP, with OpenMP tools interface with Intel. We looked at other codes like NAS parallel benchmark with Fortran. We looked at CUDA without MPI, T-Leaf, CUDA with MPI, and CUDA CUPT. Then we looked at a full real application, the Nalu wind application, the wind turbine simulation code from the exascale computing project in the US. This is primarily being developed by the National Renewable Energy Laboratory, NREL, in Golden, Colorado, and with Sandia National Labs in the US for part of the exascale computing project. Now, one of the projects that I'm working on is the extreme scale scientific software stack. It's a community effort to make open source packages available in a form that simplifies the installation of all the tools. Tools like Tau, tools like PAPI, and PETC and Trilinos, we can install them very easily in a containerized distribution and on bare metal using E4S. E4S uses the SPAC package manager. I'm sure many of you have heard of SPAC. It's a source-based package manager. It's a very mature tool. It has over 7,000 different packages that are available. And E4S is a curated collection of these tools. There are about 100 different tools for HPC and AI/ML that are available as part of E4S. We have containers on Docker Hub and on E4S website. We have base images as well as full-featured containers which support GPUs. And these include base container images, which you can start with and customize and create your own containers, or full-featured containers that already have 100 different packages installed in them. We also have a tool called E4S CL, which is the container launch tool that can be used to replace the MPI in an application that uses libraries from a container with the system MPI. And we have community policies that tool needs to conform to be included in E4S. We have many releases. These include tools like TensorFlow, PyTorch on the GPUs. They include a whole bunch of HPC tools. As you can see, we have been releasing this every quarter. Every quarter, we have an updated release, and we have containers and bare metal installation. Now, SPAC is the package manager that we use. You already have used some SPAC commands when we said SPAC load CUDA at 11.2.0. What I was saying there was, please use version 11.2.0 of the CUDA package and load it in my environment. You can use SPAC very easily by just doing a git clone, using a source, then find the compilers and external packages, and then you can just install Tau like this, SPAC install Tau. Or you can say SPAC install Tau version 2.32 with GCC compiler, with the percentage refers to GC compilers, which are found in the SPAC compiler find command at version 7.30, with MPI, with Python, with pthreads, with MPI, where MPI is provided by with the caret symbol, mvaph2, version is specified with the @ symbol, and then you can specify variants of the recipe. So each package has a recipe. That recipe tells it where to find the tool, what is the URL, how to install it, how to run tests to validate that it's working correctly. And there are a number of other options that you can provide to it, which are known as variants. So a package like Tau would have a variant like Rock'em. So you can say install Tau, SPAC install Tau plus Rock'em. Then it will use the Rock'em package and recipe from there and then install it with the support for Rock'em. So you can learn more about SPAC from this location. We have also a virtual box image and containers. And in case you are wondering about what containers are, they are a lightweight collection of executable software that encapsulates everything that you need for running a single specific task without the overhead of the operating system kernel. And you have type 1 hypervisors, type 2 hypervisors, and then containers. But you will notice the difference that while these hypervisors contain the whole virtual machine and a second kernel of the operating system, in the case of containers, we use just the bare host operating system. And when you run an application which has MPI, you run into issues where you want to make sure that you want to use the system MPI because that's the one that has been configured to use the high-speed network between the nodes. And we have support for this tool called E4S CL, which allows you to substitute one MPI with another. You can download E4S from this website, e4s.io, and download the containers like this container with CUDA or Rock'em. And you have base images, you have full-featured images, and you can start with one or the other, and even continuous integration images, LLVM, DOE, LLVM images, and there's a full documentation for how to do the bare metal installation. And we have this full-featured container that's released on Docker Hub. This is a CUDA container. You can do a Docker pull command like this. We have multi-architecture CUDA containers so that you can do a Docker pull, but you will get the right container, whether it is ARM64 or x86-64 or PPC64LE. It includes software like CUDA 12, the NVHPC latest version of the compilers, and we have base images as well, like these. And some of our images are very popular. You can see the base image for our Ubuntu, which has SPAC in it, has over 1 million downloads. Now, these are not just HPC. This is broader adoption by the Linux community. And in case you're wondering, what are these 100 packages that I'm talking about? Here is what we ship in the E4S container with 100 different products. We have support for AMD as well as CUDA runtimes. You can see these different packages that you already may be using. These are packages like HDF5, NetCDF, Parallel NetCDF, packages like Kibana, Conduit, Darshan, Dynast API. You have packages like PAPI, OpenMPI, ParaView. We saw ParaView earlier today, the visualization package, the MFEM, Magma, a range of solver libraries, all funded by the Department of Energy in the US, and some of these come from the University of Tennessee at Knoxville. And you can see packages like Tau, Sundials, Trilinos, Cocos, Raja, and Warpex, and Zeiss for electronic simulation. So we have EDA tools integrated in this as well. They rely on Trilinos. We have languages like Julia. Julia with support for MPI and CUDA. We have support for Python. We have TensorFlow, PyTorch. These are some examples of CUDA packages. And you will notice that we support not just A100 GPUs from NVIDIA, but also the H100 Hopper GPUs. You see the CUDA architecture is 90 over here. So you can just get these pre-compiled, ready to install, and deploy them on a on a Hopper GPU. Is there interest in NVIDIA GPUs here? I don't know if there is. Are your data centers also looking at?
Yeah, I mean, we have both NVIDIA and AMD GPUs.
You do have,
Pawsey,
right?
yeah. So we have NVIDIA GPUs on a cluster called Topaz, as well as in our on-prem cloud resources as well.
So if you just deploy the Singularity one file and you have Singularity installed, you will immediately get all of these packages ready to use. And here is the GFX 90A, the MI250X, which is the GPU which is most relevant for Cetonix. And you can see all these packages built for the GPU. And we have support like this. You can see an example with many of the Python tools already in your path, and you just have to say import TensorFlow or PyTorch, or you can see the versions of 2.11 and 1.13. And when I say show me what GPU it is, it does show me the H100 Hopper GPU that's in my lab. And we have binary caches, over 99,000 binaries that you can use. So when you say SPAC install a package, if you have added the mirror from E4S, then you can get binaries for the dependent packages. You don't have to install everything from source code. So you can just point to our mirror and then it will download these binaries, and they are signed binaries, so you have that security concern taken care of, and then you can just install the packages really quickly. They are binary caches. And here is the AWS image that we were using, which has all of these packages. And it also has EDA tools. Is there any interest in semiconductor design tools here? In the US, there is a huge...
Maybe a little bit to unis.
In the education?
Yeah.
At the university? So this image that you already have access to, you can just say module load EDA, and then look at all the different tools that we have. There are about 50 different electronic design automation tools, for starting from circuit simulation to GUI tools. All of these, like Magic or K-Layout or Qflow, all of these tools, or Xcircuit, they have graphical user interfaces. They work in this image that we have. So there is, besides the HPC tools that we have quite a few other tools in this image too that can be used for education. And if there is interest in teaching an electrical engineering course on EDA, we can just launch 100 different instances on AWS and just at 50 cents an hour or something, and run these tools through a web browser and have the explanation. And here are the E4S CL, the tool to launch here. And you can see what it needs to replace the MPI are three main things. You have to initialize it by telling it which backend to use, whether it's Shifter, Singularity, or Docker. You have to tell it where the image is. And then what do you do when you start up the container? The startup commands. And then you can run the E4S CL before the MPI run job, and then it will run this. We hope to have this working on Cetonix as well. So you could, for instance, replace the MPI in the container, which has OpenMPI, and launch the application with the Cray MPitch. And you can substitute one MPI with another. Here is the release of E4S CL on GitHub, the container launch architecture, and we can just log in over here. We can run this. And then here is an example for running a ecp.simg Singularity container and running these tools there. So let me just conclude by saying that you can download Tau from these URLs. A lot of this work goes on at the Performance Research Lab at the University of Oregon in Eugene and at Paratools. I'd like to thank our sponsors. I would like to thank Pawsey Supercomputing Center for enabling this workshop, and US Department of Energy, CEA in France, the Department of Defense, National Science Foundation, NASA, our vendor partners, and partners from other universities that we work with. Here are some installation guides for Tau and runtime environment variables that we use. And the Exascale Computing Project, I would like to thank them for their sponsorship of Tau. With this, I want to just quickly show you a demo of the E4S CL tool and how you can use it on the AWS instance that we have. But before I do that, do you have any questions about what I just covered? Anyone from online? Any questions? Okay, so let me show you what this Singularity container looks like and how do we use it. So if you go to the top level directory, here I'll say SPAC load CUDA at 11.2.0. This loads the CUDA runtime in my environment. Can everybody just run this command and say NVIDIA SMI? Make sure you can see the container with the GPU. We have done this before when we ran the kubectl example, right? We just load the CUDA 11.2.0. And now I will run Singularity with this ecp.simg file. Now we'll be inside the container. Now please try the command for NVIDIA SMI inside the container. The --nv ensures that you have access to the GPU. So now I'm on the Singularity prompt. I can say NVIDIA SMI. Okay. Does this work for everybody? Can you see the GPU inside the container? Again, start with CUDA 11.2.0, load that with SPAC. Singularity run --nv with the ecp.simg. And when you say NVIDIA SMI, you can see the container, can see the GPU, right? Yeah, now let's go to opt demo Python tool tests. Python tests. This has a number of tests like this f2.py, which has PyTorch. And there is a simple script called run.sh over here. So which directory am I in? I'm in opt demo Python tests. And I'm just doing run.sh. It will run TensorFlow, PyTorch, some examples with NumPy, just to make sure that Python, the full Python environment supporting the GPUs is installed here. And here is a NumPy example. Then it's going to F2, which is a PyTorch example. You'll see output that shows that it's running on a GPU. And here it says Tesla T4, which is our GPU. Then there is a TensorFlow example, and it will just run through some of these tests quickly. This is just to validate that you are able to run on the GPU, and you have a full environment where Python is in your path. You have these AI/ML tools, and you don't have to go through the whole hassle of installing all of these tools yourself. You can just do this through the Singularity container. Is this okay? Does this work for everybody? So here it's testing TensorFlow. and running the applications. Now we have other examples here where we will compile and run codes on the in the container with MPI. We'll build and run codes using Zoltan in this case. There's a Zoltan example which uses Trilinos, and we can run that. Running low on GPU memory. Okay, so you can see that it's running TensorFlow, PyTorch. It's using the GPU to the extreme. We are getting value for our money for the AWS instance where we are using this. And there it is, device name, Tensor, PyTorch, Tesla T4. So I hope this worked for everybody. This is the Python tests directory. Now I'm going to go switch gears and look at Zoltan. I'm going to / Zoltan example, and I'm going to look at clean.sh, compile.sh, run.sh, 3 scripts. I'm using tau exec-ebs to run the code with Zoltan. But let me just first do the clean.sh and then compile.sh. Okay, so now I'm compiling this Zoltan example. In case you're wondering where we are, what I did here is, just a second. I did a singularity run -- first I did a SPAC load CUDA at 11.2.0 followed by singularity run -- nv ~ecp.simg. Then I cd over to opt demo Python tests. Then I did a run.sh over there. Then I went to Zoltan and did a clean.sh and compile.sh. So I'm building this application, Zoltan application with Trilinos, and you can see that it has a number of different libraries. This has all these libraries from Trilinos. Okay, if I said SPAC load Trilinos at 13.0.1 and I said just LDD on Zoltan, you see that it's using the Trilinos libraries from here. It's using the mpich and all these libraries. In fact, let me say grep mpich, and you'll see over here mpich 4.1. And if I say LDD on Zoltan with, say, wc-l, I see it's loading 43 shared objects built with MPI. Now I'm going to come out of this container instead of running the Zoltan, and now I'm on the host. I will go to the Zoltan directory and cat the run E4S CL, say mvapich2.sh. This is now substituting one MPI, mpich, with mvapich2. Similarly, I have run scripts for OpenMPI, Intel MPI, and there's a script to not load everything through SPAC, which takes time, to unspacify it. There's a README file on how to do that. So let me run this. Here is the E4S CL command where I say use singularity. Here is the ecp.simg, but before you start the container, load this source.sh script. And what does this script have? It has source.sh, has just a load SPAC in your environment and load Trilinos. That's all. SPAC load Trilinos at 1301. And I can say run E4S CL mvapitch2.sh. This will find the mvapitch2. It will run it with E4S CL and substitute the MPI. And you should try running all three of these with Intel MPI, mvapitch2, and OpenMPI using the Y4MPI from CEA in France. And here is running the Zoltan code properly using the mvapitch2. mvapitch2 includes supports for the elastic fabric adapter, EFA, which is the network interface that connects two nodes on AWS. Here is the Intel MPI. And then you can see it figures out which libraries to load where. So you don't have to worry about it. It figures out all that itself, and it just runs the MPI application without any change to the binary. So here is a run E4S CL openmpi.sh, and it's using Y4MPI. Run E4S CL openmpi.sh, and you can see that it's using OpenMPI with no change to the Zoltan binary, where 43 of these libraries are now switching to using OpenMPI and just running it like that. So what I did here is I did a clean compile, then I did a singularity, I did an exit, so I am on the host. And then I did a cd to Zoltan and then run E4S CL mvapitch2.sh, run E4S CL Intel MPI.sh, and then run E4S CL OpenMPI.sh. So this is the whole exercise for using E4S container launch tool. And I hope you can all run these steps. This step is very critical, that you must exit from the container after doing the singularity run, and then exit from it and then run this. And with this, we are at the bottom of the hour, and I think we'll take adjourn for the day. But I'll be here. You can continue and run these tests. And if you have any questions, please ask those. And I hope you can all do this. And once I hear that you have finished with the exercises, then I will then delete all the AWS instances. Tomorrow we'll focus our attention on Cetonix and running some examples over there, and try and see what E4S bare metal install looks like on Cetonix. And thank you very much for your attention. I appreciate all of your participation, and wish you a good evening. I hope you're able to run these tests, and we will just adjourn the session now.